Hi, this is the solution for whiteboard problem 25.3. So what's the potential at point A, taking potential of 0 is 0 at great distance. And then if we bring a plus 4q charge here, what's its potential energy? What's the potential energy of the 4 charges? Okay, so I copied this over already. So this is what our setup looks like, and we want to find potential at A, and we want to find potential energy if our 4Q goes to A, and then potential energy of all charges. Okay, and what we know, so I'm going to call these 1, 2, 3, and 4. And we'll call those Q1, I guess, right? Q2, Q3, and Q4 when we get there. Okay, so we know Q1 is plus Q. We know Q2 is minus 2Q. And we know Q3 is plus 3Q. We know we need to know the distances from all of these, right? So we know R1 is going to be the square root of 2, right? Because it's the diagonal of the square. Square root of 2 times L. R2 is L, and R3 is L. This is a distance to point A. And just in case I went too fast on that, right? If we have a square and each side is L, and I want to know what the diagonal is, we can use Pythagorean theorem. And this would be the square root of L squared plus L squared, which is the square root of 2L squared, which is equal to the square root of 2 times L. So just in case that went too fast. Okay. All right, so our model is basically superposition of potential from point charges. Okay, and if we look at this, check out our book. So here's an example in the book where they're calculating the potential just from 2 charges at some other point. Find the potential of these 2 charges. And then the model is that the potential is the sum of the potentials due to each charge, right? So that's our superposition. So, if you're having trouble sometimes figuring out the charges or the models, right? So here's another one from the book that was like the whiteboard problem 25.2, but again, where you have a proton released, and then basically it's moving away. So it's released near a positive charge and it's going to move away, and you need to find its energy at some other point. And here again, the model is conservation of energy, right? So anyway, for most of the examples in Knight, he does give, see if I can find another one quick. So here's another one, right? This is actually almost exactly like the last proton whiteboard problem that we have. So modeling the system, as a proton and a capacitor, it's an isolated system, so mechanical energy is conserved. So it's really good to take note of these, and it may help you start, articulating what the model is that you should be using for each whiteboard problem. And again, it's just, how are you thinking about it? What's the model in your head for how you're going to solve this? It's not just like pulling an equation because I know this and I need to find this, right? You really want to think about physically what's happening. Okay, so then our potential at point A, given this model, is going to be the sum of the potential contributed from charge 1, charge 2, and charge 3, right? So our total potential is the sum of the potential of each charge, right? I equals 1 to 3. So potential from charge 1, potential from charge 2, plus the potential from charge 3, right? So this model leads to this equation. Okay, and then potential is a scalar, right? So we don't have to worry about directions or anything. We're just adding these numbers together. So our total, and we know for any point charge, potential is KQ over R. Right, so this is a point charge. Okay, so then we can just sum up our three potentials. So we have K Q1 over R1 plus K Q2 over R2 plus K Q3 over R3. Okay, and I don't want to write K every time. So I'm just trying to make that a little bigger for you guys. So I can factor that out. So I can get K Q1 over R1 plus Q2 over R2 plus Q3 over R3. Okay, and then now we can kind of plug in our values here, right? So we have up here that what the charges are in terms of big Q and L, and the distances in terms of L. So my total potential, use another line there, is K, and then Q1 is plus Q. R1 is the square root of 2 times L. And then we have Q2 is minus 2Q, and it's a distance L away. And then Q3 is plus 3Q, and it's also a distance L away. So we can now also factor out an Q over an L. So I get K big Q over L, and then I'm left over here with 1 over the square root of 2 minus 2 plus 3. So I get, these two would be a 1. So I get a 1 plus 1 over the square root of 2, KQ over L. And I think we can leave it like that. That's okay with me. Or you could plug in if you want to get actually a numerical answer. So let's just leave it like that for now. Okay, so that was the first part. Now we want to find, if we bring in a fourth charge to the square, what is its potential energy? Right, so we're adding 4Q here at point A. So we can use the information that our potential energy is Q times V, right? Or potential is energy per charge. So basically, we just have to take our values, or the expression we found from the first part, and multiply by the charge. So our potential energy is going to be 4Q times the potential we got before, which will be KQ over L, 1 plus 1 over the square root of 2. And so we can bring all those numbers out front, 1. And then we get KQ squared over L. And that's also the potential energy of the system. So it's the same as the last one. And that's it. Okay. Hope you enjoyed that as much as I did.